Thanks for the introduction, JJ. Just for the sake of people who watch this talk and don't really have no context of what the OpenBSD project necessarily does in this problem space with firmware versus drivers versus binary blobs and so on, I want to just add a few clarifications. So these are from an old talk by Jonathan Gray, and you should definitely, if this topic is interesting to you, you should go back to his talk from 2006 and look at the slides, because he has further things that my talk does not necessarily cover, because I tried not to repeat information that's already in previous talks. But yeah, so who here is familiar with OpenBSD and the firmware problem? Like, do you all know? Okay, so the thing is, we are not asking companies to open source their firmware necessarily. It would be nice if they did, but they don't have to. What we want to do is we want to be able to ship it to users so they can use it, and the devices work for them. We also want to be in control of our own kernel code, which means we want our own drivers to be written by ourselves, and for that we want documentation for the hardware. And the current situation is that mostly we have to rely on source code from Linux and systems like that to know what the hardware is doing, so we'd like to have a better source of documentation. To these I'd like to add my own points, just to clarify further, because some people are confused about what firmware means and what a binary blob is. So in our world, what's the device driver? We call the code that runs in our kernel. And the firmware is not on the main CPU, but it's on the device itself. And it could technically be part of the device as if it has some like a small embedded flash or onboard storage on it. But the thing is just that our kernel loads this firmware into the device and boots the device to make it run. It's very often highly privileged. The firmware will be able to read all your memory and modify it arbitrarily in many cases, which is a problem. So many people, especially in Linux world, say, those are bad binary blobs, we shouldn't be using them and they shouldn't be running. But there's not really so much we can do about that, because what we do is we write software. We don't write the hardware support code, and we don't want to write it. And we would like to have nice hardware we can use without NDAs, but it's currently rarely available. So all the systems we're using don't really have the nice properties we want. But this is just so that people who watch these talks maybe later and they see like, oh, they're talking about binary blobs, they must be talking about firmware. That's not what we do. This is the terminology we're using. So and this talk targets people who use OpenBSD, have a device that doesn't work, and would like to investigate whether they would be willing to write their own code to make the device work. I cannot really help you very far along this path, so I expect that people who watch this will be interested in attempting to walk it. I can help you get on your feet, and I can help you sort of make a few steps, but the rest has to come from your own research, and you'll have to do your own work. I actually just had this idea because a lot of people from the EuroBSDcon last year asked me these kinds of questions. So I thought it would be an appropriate topic to talk about. This is a list of things that I have done. It's not fully complete, but some of the more important points. So I've done things like, the first thing I've ever done, I think, in OpenBSD was to make frequency scaling work on the ThinkPad X21 back in the day. That was basically just porting some code from NetBSD, which was using assembly instructions to switch the CPU into a different frequency mode. And then I'd glue code around that to make it integrate with APM and so on. Other things I've done are host SD card drivers, drivers for touchpads, and a lot of Wi-Fi. And lately I've been looking into USB a bit, because one of my laptops doesn't have audio without it. So the first section here is about, not necessarily about like code, but it's about the process that people who attempt these kinds of projects can use. And what I found is, what I suspect is that a lot of people who are interested in working on drivers, they start out and they look at some bits of it and they quickly realize that it is more complicated or more difficult or harder than they thought, and they stop. And I suspect that everybody has this problem, because if you're working outside a hardware vendor, you do not have people to, you not have the hardware designers around. You cannot ask them, why is a particular thing done in a certain way? Can you explain to me how this part works, how that part works? Why does the hardware want this or that? And so you have to discover all of this by yourself, and maybe you get some help, but generally you have to sort of tinker with it, and that takes a long time. So if you do these kinds of things, you have to prepare to actually really invest a lot of time in it, and it doesn't have to be a lot of time in one big chunk, but you can keep this running as a sort of side project. Like, for example, the SD card driver I wrote took me about 2 years to complete, working every now and then. And I think that this approach, where you accept that the project is going to take a while, you're never going to get it done quickly. So you cannot have immediate success. You cannot have immediate gratification. You have to sort of roll it out and be patient with it. That's very important, I think, because otherwise you're going to get frustrated and just give up. Also, when you do your first project, pick a target that is reasonable. Like, don't try to support GPUs or Wi-Fi devices, because they're just too complex. If you've never done this, pick something that's fairly simple, that gives you a sort of like early success that you can point to and say, oh, I've done that. And then you work your way up from there. Because there's a lot of context. You need to figure out your development process. You need to figure out how to work together with the project. And all these things come on top of the work you're doing with the hardware, so it makes sense to pick something at first where the hardware is as simple as possible. Right, so these are some suggestions. They're definitely not exhaustive. Maybe you'll find other things. And generally, people start with something they already have, like a hardware device they already own. And it's probably okay to start with it. But if you are unsure whether this is really going to be a good fit for a first project, maybe do another smaller project first to just get into it. There's a lot of driver code in OpenBSD already, so you have a lot of examples. And in many cases, the drivers are actually derived from each other. So for example, the host controller, the SD host controller driver I wrote, was based on this was for a Realtek controller, which used a different hardware interface than the standard SD controller uses. And so I copied the standard controller driver as a new file, and started to remove everything that didn't apply to Realtek. And then I had this empty skeleton that I could compile, but it didn't really do anything. Which is why Uwe's copyright is still on that driver, because I didn't want to remove his credits. But actually, the drivers are pretty different at this point. But that's okay. It gives you a good head start to research what's already there and use something as a basis that already gets you somewhere rather than a blank page. Wow, what's going on out there? People are running around. Oh, yeah. Okay, so when you, like, this gives you a broad overview of how your project is gonna run. If you pick a device where there's already an existing driver, you can skip a lot of these. But if you pick something where you really have to start from scratch, it's going to take a long time, and the easiest first 2 steps, which is to attach the device and then register something that will be called when the device sends an interrupt, are the easy parts. You get that done in less than a day. But the next phase is where you actually try to power up the hardware and make it work. This will take you many months, maybe. And you will always, it's really tedious, because if you don't have documentation, you will find that you need to maybe write like some values to like 100 different registers, and you initially have no idea what they're really doing. And so you're looking at other driver code that does like lots of things, and you don't understand any of the acronyms in that code you're reading. So it's really hard to make sense of it. And you do basically a trial and error. And what helps, for example, is to get other operating systems to give you a roadmap. And it can be as primitive as just having a list of register reads and writes that this other driver is doing. And then you just go back to the source code and figure out where that comes from, and then you implement something like that. And eventually you will have the device up and running, hopefully. And maybe you have to load firmware as well for this. It depends. It could be part of the init sequence. And eventually you get an interrupt. And then you know something is alive on the motherboard. I can talk to something here. That's great. And this is the first milestone you want to reach. And from there on, it's another couple of weeks or months of just running into another problem and another problem and another problem. And it never stops. It just feels like it's going on endlessly, endlessly, endlessly. And you almost give up. And eventually you find like one more bug and you think, oh, finally it will work. Then no, there's still another bug you have to find. And then suddenly you expect that you still have like 10 bugs to solve, but suddenly it starts running and working. And that's great. Like that's after such a long time of work, getting something to work gives you a real rush. It's really great. Yeah, regarding setting up the environment, so you want to test your device on a dedicated machine. You don't want to edit code on the same machine because you're going to crash it all the time. So really use two machines. And also make sure you have something sane regarding management of source code, because if you have a project that runs for a few months, you will lose track of things if you just save it as a diff. Everybody can figure out their own process for that. I guess a lot of people use Git or similar tools. Whatever you do, try to find something that works for you. It doesn't matter what you do, but have some independent source code control of the changes outside of OpenBSD's view, because you will need it for yourself. And nobody else will need that. I can show you some of my own histories if you want. Personally, I use Fossil for these things a lot, but you can use whatever you want. And also you should try to interact with the project. You initially won't have a lot of things to show maybe, but you can probably start reading a bit and keeping track of who might be interested in helping you out by figuring out which people are working within your vicinity. And that is a big part of becoming involved, is learning who people are, what their moods are, when you can contact them because they're in different time zones and all that. And you will learn it by just following them and asking questions. I'm not going to say a lot about licensing. It should be pretty clear that we're very strict on accepting only ISC licensed code. So please respect the author's wishes of code you read as a reference, and do not copy it if they don't want you to copy it. But also inform yourself whether in your jurisdiction you're allowed to use code and binaries as a reference for reverse engineering. And because that's important. You should be free to do that. I think everyone should have the right to do this. In the EU, we have a special exception in copyright law, which I put here. But you should make sure that this applies to you as well. Okay. The one thing you should never do, which will eventually happen if you're working in drivers a lot, is you'll be offered exclusive access to some bit of information by signing an NDA, which means that you cannot tell me or anyone else about it, and that breaks our code review process, because we cannot review code based on the same basis of information. And that is bad. So people will want to be able to talk to you, ask questions of your understanding of the code and your reasoning. And if you are hiding that behind an NDA, then nobody can access it. And that's not a good idea. So you can use any published data sheets and leaked data sheets. You can use source code as a reference, and you can also do your reverse engineering if you want. But the most important part for OpenBSD is that if you present yourself to someone to say, I'm working on an OpenBSD driver, and they ask about NDAs, you should say, no, we don't sign NDAs. It's very important for us. However, you can get information that is behind NDAs by asking people who have signed them. And I've done this a few times already, and it works. It's very good because you free some bits of information. You don't necessarily get like a data sheet or something, but you might get small excerpts from them. Because if you ask a very concrete question to an open source programmer who's working at some company, and you just find their email address somewhere on a mailing list in Git, or Git is great for that they put email addresses in all the logs of the Linux kernel. That's awesome, so you can just mail them all. And just ask. And I've had responses from people at Intel, Realtek, and other companies like that. And it works well if you're not making them do any work for you, but you're just asking nicely and present it as a problem case. And I followed up some of these, when I got positive answers, I followed up sometimes asking for documentation, which they then said they cannot share. And I said, okay, that's fine. And then they said, well, it's okay, you can always come back and ask. So by building these sorts of like little entry points into these companies, we can actually, as a community, also get information that we need. For example, the one bit of information that was shared with me was that on the ASD host controller, sometimes the host controller will send cards, commands to the card that the software stack will also send. But you can also disable that feature. But it's like sort of like a hardware acceleration, if you will. But if you don't know that, you're trying to access the card, and the host controller does something magic behind your back, and the card gets confused. And so without having somebody to tell you, well, you should just register to the value 4, and it will stop doing that, and the card will work. How can you figure that out? It's difficult. When you're eventually done and you have something working, you submit it as a diff. If you do this for the first time, don't be the guy who sends a diff to the mailing list and then it doesn't apply. It happens maybe once a week for us. Just try to mail the diff to yourself and apply it. And if it doesn't work, fix your mail client. Yeah, some other things are obvious. I mean, you should work against current and so on. You can read that up. Some things which aren't really necessarily documented well in other resources is that you should, this is sort of like folklore knowledge, do not cause regressions for other devices. In a lot of cases, sometimes this is impossible because you have nobody to test a particular device. What I've done partly is that I went on sites like eBay and just bet like €1 on a lot of Wi-Fi dongles and eventually got a few of them. So I just got random versions of random hardware to test with. You can also ask people to test the hardware, and they will often do it. You test your diff on some existing piece of hardware that already works. That's very important because if it turns out later on when your diff got committed that it broke something, it will be backed out. And very important is also that you learn how to build your own OpenBSD release and do an upgrade with that and an install, upgrade or install. And you make sure that your diff doesn't break it. And it can be really, really subtle. Like, it can be that the install process works halfway through and then suddenly your driver throws some error because the Ramdas kernel is a bit different to the generic kernel. And you want to make sure that such differences are tested before anyone else runs into them. So please do that. And so for me, I try to, any diff I mail out has been run through my build box. And then I have done an upgrade somewhere with it. And then I have tested it after the upgrade. I think that's very important, and it's only fair because if we don't respect the testing environment that other people need to make progress, you are blocking everyone else in the project from making progress. And also, once you have it in the tree, you should prepare some time to make sure you react to feedback. Because we will need people around to look after the code. We cannot use code that has no maintainer. It will eventually be deleted. It should be possible to reach you. Even if you say, I don't have time right now, that's fine, but make sure that you're open about communication back to the project about problems that people find. Oh yeah, and sometimes, the last point on the slide, if you try to be too helpful and too nice, sometimes you get overworked with it because you might get 5 or 6 reports. You don't see a lot of these on the list. You see them sometimes. But some people tend to mail people privately. And so for every bug report you see on the bugsat list, developers get maybe 5 or 6 of those. And so if you try to fix all of them, you're spending all your time just fixing other people's problems. And if they are lazy about providing details to you, you have to go keep asking, and eventually it gets very tedious. And sometimes it's okay to just let something slip and say, I cannot reproduce this bug, I cannot fix it, it's not my problem. because otherwise you get worked out. It's just not possible to keep up. You just want one person. Yeah, make sure to follow coding style. There's a man page for this. There's some other points here. We tend to use very few C files per driver. Other systems tend to have like a subdirectory with many C files. Those are just like little things you'll see also when you look at the existing code. Just try to make things as consistent as possible with what's already there. If you're porting like a driver from FreeBSD that has like 10 files, try to merge them, for example. Okay, so far the process stuff. Can I get a sip of water? A small break. Okay, so these are all pointers to things you should do research on. I'm not going to explain in detail how many of these things work, but my goal is to give you an overview of what kind of topics you will have to look into so that you can make a list of things that you've researched. So the first thing you'll see when you look at driver code and try to figure out how the driver gets started, you will get into the device framework. And that is documented in AutoConf. And there's a couple of other man pages as well linked from that. And basically, what this is responsible for, it's for managing the device tree. So it attaches and detaches devices at runtime and at boot. And it provides mainly 4 entry points from the config framework to the driver, which you have to implement. Every driver has a struct that represents its global software state. And that struct exists once per instance of the device in the hardware. So if you have like 2 Intel Wi-Fi cards in your box, you will have 2 of these, 1 per device. And this is basically your driver's global state. You can put anything there that's shared between functions. And there's a lot of examples in all the drivers. And the naming is just a convention. So if you follow the naming with the soft C and so on that's given here, people will just read the code and not wonder what this is about. This is fairly standard, like a good idiom to use. And some of this is managed by the device framework for you. So for example, your device name shows up inside this struct in that member. That's just one example. The other things, you can add whatever you want, whatever you need. Any shared state between functions goes here. You will have to add your device maybe to the PCI or USB database. These are the steps to do that. It's fairly simple. There's a text file that contains a long list of vendor IDs and their hex value that was assigned to them, and product IDs. And you edit this file, add 1 line for your device, run make. It will generate new C files that will be included in the kernel, and then you can refer to your device. That's pretty simple. Like sometimes this is enough to make one device work, if it's just shipped with a different vendor and product ID than the standard reference design uses. So in a lot of cases, you get some Wi-Fi chip, and it is from some company, and you don't really know what's inside. So you go on the internet and look up the USB device ID, and you realize, oh, okay, this is actually a device that's supposed to be supported by the URTWN driver, but it's just not in the list. So you add it to the list, plug the device, it works. If you've done that, you've done a great job, and you can mail the diff, but you haven't really done any driver development. But it's a very good start. So how does software talk to hardware? I think that's something that a lot of people who write software might wonder about because they have never done it. But it's actually fairly simple. So the software interface in hardware is usually or always a set of registers that are basically just units of memory that have some meaning for the device. And by writing to these, you set bits inside the circuitry of the device that make it do a certain thing, or make it configure some of its operational aspects in some way. It can also provide you feedback through these registers, so you read them back, and the device tells you something. These are usually between 8 and 64 bits. They can be read-only, write-only, read-write, and sometimes they clear themselves if you read or write them. They can also be big and little endian, so be careful. You have to keep converting between the host byte order and the device byte order. A good idea for this, to catch bugs in here, is to put your device into a Spark machine and see if it still works. So the thing is that every device has very specific registers that don't appear in any other device. So the driver's job basically is to make any set of weird register combinations appear as like a network card or a mass storage device. And it's the job of the driver to understand how the registers are laid out and how to use them to make the device operate. And without documentation, it's pretty hard to know what to do. So you cannot brute force this, it's impossible. You have to have some reference. I would recommend that you try to find data sheets, even if you have low hope of finding any, just Google around a bit. I've found a few things like that. And you can also look at open source drivers. If you're doing your own reverse engineering to derive open source drivers from proprietary hardware, you probably wouldn't be here in this talk. So these are the sources that I regularly use. I don't actually reverse engineer any binary drivers or anything like that. I don't have the time for this. But this really works if you're lucky and you find a good reference. So you access registers with a special API in OpenBSD that's called busbase, and basically it hides lots of architectural differences from you. And so you don't like actually have a pointer to the register, but you tell this function which address you want to access on the device. And usually the registers are going to be like in one or more contiguous memory spaces. And you identify a register relative to some base offset. And that base offset is provided by the machine, like it's set by the BIOS or by the PCI subsystem. And so your function is going to take like a register address, add the base address to it. This is actually the bus space is going to do that for you, and then access the device register if it's like mapped in memory at a particular point. And then you can read and write them. Some devices also require you to do a transfer sort of thing. So it might be that you cannot actually access a register unless you go through some other register. Like you write the address of one and of register X into another register, and then the value of that register X appears at a different location again. That happens quite a lot. And yeah, some buses like USB don't give you that kind of access, so you have to use USB transactions to do anything. Another common idiom is to poll a register. So this means, this is usually done in early stages of when you bring the device up, so that you don't have interrupts operational already and everything. So basically it's a busy loop that will spin on the CPU. You tell the device to do something via one register, and then you read back another one to see if it's done it. And eventually you either you succeed and you exit the loop, or you time out. And then you print a device timeout message to dmask, which you've probably already seen, and then give up. So the thing is that this blocks the kernel, so you shouldn't really do it a lot. It's okay to use in early device initialization, and sometimes it's used a bit too much. Like in the Realtek driver, there's a spot where I'd like to remove it but can't. But you will, if you have a too large delay, you will notice a brief system hang. So generally, for real input-output, you want to use DMA, because most devices nowadays do that. And the way this works is that the device has logic inside which knows how to fetch data from RAM and write back to it, and it operates independently of the CPU. And so this is called like a small DMA controller on the chip on the device, and you have to program that controller with an address and a length, and it will do a read or write to that address to that block of memory depending on configuration. And at the end, it will send an interrupt and say, I've done it, your data is now there. And then you can go read it, or before, yeah, if it's sent you data, you read it, and you read it through the virtual memory address space of the kernel, because the BSDMA API gives you a way of viewing that physical memory that the device wrote to through basically a pointer that you have in your kernel program. So you get your pointer returned from BusDMA, and once the DMA transaction is done, you can go to that pointer and find the data that the device has written. So there's an example in the BSDMA man page, and there's lots of examples in the tree of how to use this. If you have any half-series device, you will have to get familiar with that. Another thing you need to know about is that in the kernel, there is a concept of going to sleep or sleeping, which means that you're basically yielding your current sort of execution and tell the scheduler, I don't want to run anymore. Did you see MPI's talk yesterday? That's what he was talking about. Except the drivers do it too. He was talking about Firefox, but the drivers can do the same thing. And there's a function called tsleep, which will make a thread go to sleep. And there's a function called wakeup, which will wake up a particular sleeper. So the way they're identified is usually you have like some pointer, like the pointer to your global state or the pointer to a variable in your global state, and you say, I sleep on that. And then the wake up uses the same address to wake up that particular sleeper. That's how it's done. So it's pretty simple and works pretty nicely. Interrupts are a way for the hardware to talk back to us. And basically, it's like your driver is going to be event-driven from interrupts. And when you register your driver, you establish your interrupt handler with a PCI or USB bus or some other potential bus. And whenever the device signals interrupt, this function will be called. So there you have to understand which registers to read, where to get information about the event, how to handle that event. And maybe you have some other thread in your driver that's waiting to be woken up, so you wake up that thread and to handle whatever needs to be done next. And in this interrupt context, you're in a special context in the kernel with its own stack and everything. And if you sleep there, you will hang the entire system. But DDB or the kernel will make pretty sure that you're never going to try to do that, because if you try, you get a lot of white text on blue background. So you will probably maybe make that mistake, but it will be caught easily. Another thing that's in the kernel toolkit is the concepts of timeouts and tasks, which are sometimes used in drivers. We try to avoid them mostly. OpenBSD does not use a lot of SMP yet, so contrary to other systems, it's often okay to do a fair amount of things in interrupt context. But in some cases, it's just not enough, so you have to sort of create another execution context where you're allowed to sleep. And so timeouts and tasks can do that. Timeouts are also useful for a different thing. If something is occurring periodically, you can register a function to be called every second or every 2 or 50 milliseconds or whatever you want. And it will always be called at about that time. Yeah, so the tasks are good for creating basically another context that is allowed to sleep. And the tasks only have a process context, basically. Their only purpose is to be allowed to sleep, really. The timeouts, you can choose whether you want a process or an interrupt context. So they're fairly flexible. For some reason, USB has its own tasks, because the task add API is younger than the USB stack, I think. So there are some exceptions there, but you will see examples in drivers too that you can refer to. So you've had interrupts, you've had these tasks and timeout you might have running around in your driver, but you also have user space programs poking down into the kernel to ask it to do certain things. And that's yet another thing you need to worry about. And so those are IOCTL handlers. They run in the process context of the calling process. So you can actually sleep in there, which is useful. And its job is to change configurational aspects of the device. For example, bring the interface up, or I don't know, OCTL like configures rate parameters to these interfaces and so on. But you will have to have a handler for this, and you might have to relay requests to the upper layers in the kernel if there's like the Wi-Fi stack or the network stack or whatever. Yeah, that's pretty much it. So the important point here is that because this is inside the user space process context, which has now entered the kernel, it can happen at any time, and it's racing all your other execution contexts. So for example, there's no guarantee that no interrupt will happen during an OCTL. You have to take care of that not happening, and that is what you use the SPLs for. So the system priority level disables certain class of interrupts, always the one you want to disable plus some other lower priority ones. And so there's a fixed set of names of classes of interrupts you can block. And whenever you have a data structure, like in the softc, for example, which can be accessed from both interrupts and from other contexts, you need to use the SPL. You'll see a lot of these. I think in other systems like FreeBSD, they're not as relevant anymore because they use a lot of threads for interrupts nowadays. But for us, it's still like the thing to do that. And the API is pretty easy. You just like call a function to block interrupts of a certain level. You get an integer back. You don't look at that. You just pass it back to the SPLX function later to restore the level that it was at before your call. So just make sure that whenever you access something that you have in your interrupt handler, you wrap it in SPLs. This is a neat trick that DLG showed me. It's not actually used in any driver yet, as far as I know. I'm just putting it up here because it's not documented anywhere else. You might not have to do this. But I just wanted to show how you can keep track of your tasks that are running in your driver's context so that you don't have problems with synchronizing them, for example, with the OCTL configuration request. One driver which has a lot of problems with this is IWM, and I've been trying to fix that for a long time now, and this is one of the proposed solutions. And I have a diff for that already, but it's not committed. If you end up having questions about this, you're already far enough that you won't be sitting here, but you'll be sitting somewhere at your desk and working, so just refer back to this and ask me questions if you ever run into it, if you ever need it. So if you use multiple tasks in your driver, try to make sure that when you bring the interface down, that no other threads are still running, and expect the hardware to be up, which you've just reset. This is why IWM sometimes prints blue lines into dmask, and they're all spurious sort of arrows of tasks that are still running, but they shouldn't be. A lot of devices use firmware, which you talked about before. This is just to show you where things are depending on what kind of license your firmware has. So if it's a good license, it can go to the sysdev microcode directory, and we can ship it in the base system, so people don't have to do anything special to get the device working. There's not a lot of devices, unfortunately, which have suitably licensed firmware to go to base, so a lot of them are banished to ports and will be installed with FW update. The downside is that people cannot use the device during installation because they don't have the firmware on the system yet. But, well, there's only so much we can do. You should really try to, if your device is in a laptop, please implement suspend resume handling, because if you don't, then you might break it, so that people who are happily using their laptops now have a new working device inside, but they cannot suspend resume anymore. And the way this works is surprisingly simple. The first time I've had to deal with this was in the SD card driver, and I remember asking someone like, I think it was Mike Larkin, I asked him how this works, and the nice thing is that the ACPI framework handles most of the things for you. What you can do in some devices, like what I do with the SD card reader, is you just save all the registers to somewhere in the softc or somewhere else, and the system shuts down. And then when the device comes back, your restore function is called, and you just rewrite the entire register space. And then the state of the device is restored, and you resume from where you stopped. Any other upper layer operations like IOs and something will already have been stopped, so you don't have to worry about those. In some cases, though, you might have to stop the device, power it down, and reinitialize it. Like, for example, that's what IWM does, because there's no way for us to keep the firmware state intact. Good, so that was some of the programming concepts in the kernel that you need to know about. This section is about debugging. I found that my skills in debugging have gradually increased ever so slightly with time, simply because it never stops. You always have to look at the next problem and the next problem. And there's a couple of tricks you can use here. So if you can get a serial console, I know a lot of laptops don't have them, and your devices will be inside those laptops, but you can actually, you know, get like an APU or something like that and get the same device on a different card, like a PCIe card, and then use that separate device with a serial console for development, because it's a lot easier to debug things. If your machine freezes up and you can't even type in DDB, you've basically lost. Another nice thing is that you can use the bsd.gdb kernel image to get much nicer backtraces from GDB when your driver crashes, so you can actually see which line it's crashing on in C, which the default GDB doesn't do yet. Jasper was hinting at this in his talk, that they're working on that. But for now, you have to boot that large bsd.gdb kernel, which is a lot bigger than the standard one, so it doesn't run on all machines, but most modern machines will run it. You can also use printf, but sometimes it hides bugs, because printf, for example, will change the interrupt protection level to SPL high, which is the highest level. And doing an SPL operation tends to take some time in the hardware, like relatively speaking. So you're introducing latency, and some behavior you saw without the printf might now disappear. And this is pretty annoying. A lot of drivers have a lot of dprintfs inside of them, and you can usually enable them by defining some macro, like a debug macro. And then there's also an integer you can set to enable some or all of these printfs. And I was always recompiling my kernel after changing this integer setting, and then I think MPI showed me a nice way to just set it at runtime like this. So you don't have to actually recompile just to get the printf level up or down. You can do that at runtime. Yeah, and did I mention that it takes a lot of time to find problems? Yes, you will spend a lot of time. And it never stops. And surprisingly, a lot of the bugs that I've run into, that you sort of like have this hardware, it doesn't behave the way you expect. So the natural reaction is to say, well, this hardware must be broken, but usually it's not. Usually you have some bug in your code that is responsible, and you have to track it down. And oftentimes when I thought like something is like, I don't know, it could be the compiler, it could be the hardware, it never was. So most of these are pretty simple C coding bugs that also happen in user space, right? So you have uninitialized variables quite a lot. You have simply wrong code that does the wrong thing instead of what was intended, off by once, and math errors in the calculations and so on. Use after freeze are really hard to track down sometimes. Race conditions are difficult, but you also have all of these in every program. What's specific to drivers is that sometimes you can cause erratic hardware behavior by simple bugs that are subtle, like you're writing the wrong bits, or you not doing something the hardware wants you to do, but you don't know that it needs to be done. And that is a very difficult to find bug. I have some examples of bugs just to give you an idea. So some of them were recently fixed. So for example, the RTWN one here, the first one, what happened was that somebody reported that the Wi-Fi interface had stopped working, and eventually I figured out that if I compile it with no optimization, that it works. And then the assumption was, okay, we switched to Clang recently, so something must be broken in Clang. And so people told me, yeah, isolate the function in the file which is causing this problem, and then we'll look at the assembly and figure out what it's doing. And so I did that, and I eventually ended up with assembly that I could compare between GCC and Clang, and I asked Katenis to look at it, and he said, well, they look fine. Both look fine. And but it still didn't work if I compiled it with full optimization. So I kept poking around at it, and meanwhile, Jonathan Gray was compiling this problematic file with different compiler options in Clang and different compiler options in GCC 6. And GCC6 eventually said, oh, there's an uninitialized variable. And what had happened was that, so there's a calibration function that runs periodically to keep the radio happy, because you have to do that in Wi-Fi sometimes for some devices. And that is doing 3 passes. It expects the results of the calibration to be stable after 3 passes. So it does a pass, it reads back the results. If they're the same as in the previous run, you stop. You're done calibrating. And in this case, you also have to save some registers from the device context before you start calibration and restore those afterwards for some reason. And so what I did was, what the code did was it did before the first pass, it saved the registers on its stack of this function, ran the calibration, and returned. The second pass, this function was called again, and it didn't do anything with the register state. It just sort of like ran the calibration pass. And then the third time it was called, it would do the calibration and then restore registers from its stack. And if you know how this works, you will realize that we were writing garbage bits from the stack of the third function call into the hardware. And surprisingly, if it's compiled with GCC, it still works. But if it's compiled with Clang, it does not. And I always had like performance issues in this driver, and they were all weird, and I could never figure them out. And after finding this, they were all gone. Everything was good. So sometimes it's good when things fail hard instead of like failing softly. Yeah, and there were things like copy-pasted lines that got wrong. I mean, sometimes you have like large lists of hex values that you have to copy into the hardware, and oftentimes nobody really knows why they are that way, because what the manufacturer did is they measured the behavior of the device in a lab, and they tested out some settings, and they found that these settings work particularly well under most conditions, so now they're using them, but nobody really understands because it's like a circuit, and nobody understands all the things it does. And so that you end up with like some magic init values that you write at the beginning of the hardware, and you know that the vendor found those to be particularly good. What I did was I copy-pasted one line wrong, so the first line was duplicated, so all the following hex values were wrong, and the device didn't work anymore. Another thing about this chip is that if you reboot it and you try to interact with it over PCI, if it's not rebooted yet, it will hang the entire machine because the PCI bus seems dead or something. I don't know. But there are all these sorts of quirks where you sort of figure out what's wrong, and afterwards it's sort of obvious, but before you find the cause, it's very strange. The SD card driver, those were the last 2 bugs I fixed before it worked. The first one was actually found by a Realtek engineer. He looked at my code and said, oh, you're writing, you're not setting a sector size. You're setting a sector size 0, but the sector size should be 512. Oh yeah, obviously. Okay, so now it should work. Oh no, it still doesn't. Because I also told the hardware to read when I wanted it to write, and vice versa, because I had a bit flip in the macro. And off by one example was recently in the new XHCI code I wrote, where you give it a couple of descriptors that describes the transactions it's supposed to do, and it's going to do a couple of them, and at the end of the last one, it's supposed to send an interrupt, and the device checks this interrupt on completion flag on every such transaction, and if it's set, it sends the interrupt. If not, it does not. What we did was we only gave it the all but n-1 descriptors and never got an interrupt. So I was sitting there and thinking, why is this hardware not talking to me? And it turned out that we were simply like having an off by 1 in the number of descriptors we were giving it. Yeah, so this IWM bug here is an example where I didn't know what the hardware was expecting. So there is a bit in a register that configures the reception of packets. And this bit says that you should get 1 interrupt per packet. And Linux uses a different way where it aggregates a couple of frames and processes them in a batch. Whereas our code was written in the old style that Linux was also using years ago. But since they implemented the new way of doing it, the bit definition was removed from the Linux header file, so I couldn't see it. And so eventually, the Intel engineer who was helping me a bit with this said, oh, look at this Linux commit from 2 or 3 years ago. You need to use that bit that we removed in that commit. And I don't think I'd ever have found this, because I was already looking at this for like a week and not figuring out why I can't receive any frames. So it's almost done. Yeah, and then another IWM bug is not so important. It's just another thing where we told the hardware to do the wrong thing. So this is most of what I had to say. This is Henning presenting a little flower. I thought it was nice to use this for this section, because this is a list of other presentations you should look at if you're interested in this topic. There have been a lot of them, in fact. I went to the papers, to the events page, and looked at all the papers there and listed all the ones that are related to hardware development, driver development in some way. So there's a lot to read, and you can also watch some of them on video. So if you need more resources, then these are interesting, and these are also interesting. These are more about very specific devices. The others are more generic. You can find this slide online later, and then you can go back and look at the others too. You can do further reading in drivers, of course, for OpenBSD and for other systems. A couple of MAN pages, just references I used inside the slides before. And also there are books about driver development. There is no book about OpenBSD driver development, but a lot of the concepts from these other books, like for Linux and FreeBSD, they will translate well. I've already talked to people who recommended, what was it, Linux device drivers, edition 3. I think you can find that on lwn.net. And then there's also a FreeBSD driver book by Joseph Kong, which you might want to read. Because this is like a difficult topic, if you're entering it, it really helps, I think, to like sit down and read a book like while you're on a train or something and just get the concepts in your head. And once you have that context knowledge, it's much easier to read the code and make sense of it. Okay, that's it. Thank
you. We have the first question here already.
Yes. When you boot into a bsd.rd, it doesn't load the firmware you already installed on your base system. Could it be something that could be fixed via some reach around that, say for instance you have a Wi-Fi driver that needs firmware and you want to grab the packages over your Wi-Fi interface because you're on the road and you still need to do the update?
So if you're upgrading, then it does that.
The bsd.rd doesn't load the
No,
firmware.
it does. If you're installing, then it won't. But if you're upgrading and you go to the point where it gets to mount the root disk, it will actually load the firmware from there, because the kernel has a special hack to look and mount etc firmware and not just etc firmware, but only in BSD-RD. Okay. And so this is why if you, like, for example, use IWM, it will not find the firmware first because it boots without the root file system mounted. And once you go through the installer and say upgrade, and you enter, eventually it goes to mount the root disk. And then you will see a message that says, oh, I found my MAC address. And that's because in IWM, we cannot read the MAC address without first loading the firmware because of the device. That works that way. And so in that case, you will actually see that the device is coming up after the root file system has been mounted. And then it will normally work okay from there. You might have to escape to the shell and maybe run a scan or whatever if it doesn't work. Okay. But generally, if you're upgrading, then most devices will just operate fine as they do in the installed system. That's the idea. But if you're installing, that's a different story.
Any other questions? Yeah.
Thank you, Stefan. Awesome talk. If I can add one piece of advice, remove invariants. So if you're working on a wireless driver, set up a spare access point with no crypto. Make sure it works. Then set up software WPA. Then make sure it works. Make sure no crypto still works. And then move on to hardware acceleration. Make sure all three still work, and so on.
Yeah.
Then
definitely.
Also another thing. I mean, this is also relevant for if you check storage drivers. Don't put your important data on the disk which you're trying the controller on. I mean, where you were the driver for the controller. Because if you do a write instead of a read, then you lose your data, basically. And the other thing is, other BSDs sometimes have virtually identical drivers. Just sometimes some function names change or whatever. It depends on the history of each BSD, so it's sometimes possible to just take one driver from OpenBSD, put it on Net, or the other way around, and it will just
Certainly.
work.
Yeah, definitely. Use any existing code you can find which has a good license, of course. Granted that. It's very important because you're saving yourself a lot of time.
Any more questions?
I have a question. So I have a device here which was given to me by our friend Remy. And it's a temperature sensor. And it will, if it has a driver, it would print, it would give you two sensors in sysctl, which show the humidity and the temperature. And there already is driver code for earlier versions of this hardware. So it should be fairly easy to get this one working. And my idea was to offer this device to anybody who wants to try to make it work. And I would give you a deadline of 4 weeks. If you have a working diff on the list in 4 weeks, you can keep the device. If you don't, then you send it back to me or to somebody else who wants to try. So does anybody want to try it? Only one? Okay, it's yours. Let me know in 4 weeks how it goes.
4 weeks, okay, from now on.
Yeah.
I'll CVS up during the time and I get the device out from you.
Okay, thank you.